Hey guys, welcome back to distance learning. Um, since I'm not here to go over these problem sets with you in person, I'm just going to record myself doing them. If you continue to have problems, please let me know. Okay, um, let's look at this. Let's go with this first one. The rate of the reaction of oxygen plus NO2 goes to NO plus O2. Was studied at a certain temperature. The first set of experiments, NO2 is in large excess with a concentration of 10 to the 13th molecules per centimeter cubed. The following data is collected. All right. So basically, that's just saying there is a whole bunch of NO2. When that happens, we can change the, we can look at the concentration of oxygen atoms without worrying about NO2 changing its concentration. It's always going to remain pretty freaking high because it's a lot higher than the oxygen. So let's go on with this. How do we figure this out? What is the order of this reaction with respect of oxygen atoms? So anytime you see time and atom, or time and then concentration, this is going to be using the integrated rate law for these guys. And remember, the way you can tell using the integrated rate law if something is first, second, zeroth order is how do these guys look on a graph. So anytime that you see a straight line, you know, okay, it's this order. If it's just the concentration to itself, then you know it's zeroth order. If it's the the natural log of it, then it's first order. If it's the reciprocal, and the reciprocal is kind of weird because it actually goes up this way, then you know that it's second order. How does this help us? Well, anytime remember what this is. This is this table is, you can actually plot out this table. Here's time, here's the concentration. You can plot this out to see is this you know, does this look the same? So this time frame jumps pretty evenly, right? It goes from 0 to 1 times 10 to the negative second, 2 times 10 to the negative second, 3 times 10 to the negative second. So if this is a linear decrease, we should see the same thing here. These should be going down at the same rate. What's the difference here? So here we are dropping by, what is this change? 3.1? Or is that 4.1? No, it's 3.1. So yeah, 3.1 times 10 to the 9th. So that means that this drop should also be, if this is zeroth order, then this drop should also be 3.1 times 10 to the 9th. What does this turn out to be, though? I'm going to move these decimal places over to put them at the same thing. So 1.9 to 0.68 is not 3.1, whatever that turns out to be. Let me grab a calculator real quick. 1.9 divided by 0.68, or minus 0.6. So this is dropping by 1.22 times 10 to the 9th. So that's not it. And what is this? How does this drop? So 0.68 minus 0.25. And this drop is 0.43. So as time goes on, we know that this isn't linear. In fact, let me show you this to be the case. Geez. it didn't do the thing I wanted it to. Time 0, 1, 2, 3. And then here, this is going to be our concentration of O. And what were those numbers? 5.0, 1.9, and 0.68, and 0.25. Okay. The reason I move the decimal place over is because we have different orders. I just converted these times 10 to the 8ths to 2 times 10 to the 9ths in order to make everything nice and neat. So if I wanted to go through, I could actually insert a chart and see. Yeah, this is definitely, most definitely, not a straight line. Huh. What do you think about that? So then we're going to do the or the natural log of O as well. I'm going to actually make this a little bit larger for you guys to see. There we go. So what I'm just going to use this spreadsheet, but here what I would suggest doing is taking the natural log of O and the reciprocal of the concentration of O, and just in your calculator write out these numbers. And you can kind of use a extend this table out a bit. Because on the test you're not going to have a spreadsheet. But I do. Haha. ln of the following. And bring that down. Cool. So now I am going to insert a chart for this guy. Hey, and this guy looks pretty straight. This guy looks real straight. So it's probably first order because of that. Now, if you obviously you don't have, you won't have a way to graph things out like this on the exam, but you can do the following. So here, again, we're going from 0 to 1 to 2 to 3. So these should decrease at the same amount each time. So going from here to here, what does that actually turn out to be? Oop. So each decrease is about 1. Right? 0.96, 1.02, 1.00. So all of this is about 1. So that looks pretty good. And you could do that kind of in your head. You can go, okay, 1.60 to 1. Okay, yeah, that's 1. Here to here is about 1. And then here to here is about 1. So that can be your way of realizing, oh, this is this natural log line is going to be straight. For sake of completion, though, let's go through and do the reciprocal of these guys. And again, you can kind of go through and do this since you in your calculator. 1 over this. And do that. And kind of realize what's happening here. So here you're going up by 0.3, here to here, way more than 0.3, and here to here, way more than 0.3. So we know that this is not going to be straight. So that's how you go about and figure out the order of this reaction. It is first. So since again you don't have a spreadsheet, my method for this for you guys would be to extend this table out and do natural log of O and the reciprocal of O concentrations. And then do the natural log of this number, and then do the reciprocal of this number, and fill this out. And then try to figure out, as this thing is going down in time, do these guys decrease or increase at the same rate, at the same amount? So here we're just going, 0 to 1, 1 to 2, 2 to 3. These should be going at the same amount each time. All right. So that's how we go through and do number 1. Number 2, the reaction is known to be first order with respect of NO2. Determine the overall rate law and find the rate constant. Okay, so we know that it's first order in relation to NO2. So they're wanting to know the rate law, right? Reflexively go through. Rate equals K, concentration of O, concentration of NO2. So they told us that NO2 is first order, and we found out up here that O is first order. Okay, so this entire thing is second order. All right. And now how do we figure out the rate constant of this guy? So from this, we can go through and find the slope of this line. Okay. And I know what you're thinking. Geez, how can we figure out the slope of this line, right? I mean, it'd be easy with this, you can just go through and find our trend line, and find the formula in this. In a spreadsheet like this, but we don't. But remember, what you can do is do the, what is it called? Y2 over X2 minus Y1 over X1. This is a way to find the slope. Remember, the slope of these guys equal K. And so we can just kind of pick right here. So we can do, let's do these two. And so we can just put Y2 is going to be negative 0.385 over X1, which is 2. Just 2. And then minus this 0.4 over 1, and then go to town from that to figure out what this slope actually is. All right, so maybe I did that backwards. I don't remember. No, that's right. I feel like I did this backwards, though. Negative 0.385. There we go. Divided by 2. Minus 0.64. Yeah, there we go. Yeah, it's negative, because its slope is negative, negative 0.83. So that is going to be our K. Oh, sorry, positive. 0.832. It is positive because remember, k's are always going to be positive. Refer back to the cheat sheet I gave you and look at what the slopes are on the integrated rate law. All right, so let's do number 2. The composition of a certain insecticide in water follows first order kinetics. So right off the bat, we know that this is first order. One thing we might want to think about is pulling out our constants and equation sheet and refer to this. With a rate constant of 1.5 per year. The quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5.0 times 10 to the negative 7th grams per centimeter cubed. So here's our concentration. What is the concentration of the insecticide on June 1st the following year? So our time is 1 year. So that's going to make things a little bit easier. I'm going to change this up a little bit. The concentration of the insecticide at a certain time is going to equal the concentration of the insecticide initially, e to the negative kt. This is the form of the equation I'm going to use. I just basically took everything to the power of e, or e to the power of everything, to get this. Okay, so then what do we need to do? We're looking for the concentration at that time. We have 5.0 times 10 to the negative 7th, and then e to the negative k, which is 1.45 times 1. All right, so let's pull out our old calculator and do this. So negative, this calculator doesn't like it when you do that. Negative 1.5 times 1 e. Great. And then we're going to multiply that by 5.0 exponent negative 7 to get this. 1.35 times 10 to the negative 6th grams per centimeter cubed. All right. I mean, it went down a fair bit. It went down a fair bit, an entire order. So that's good. That's good. But yeah, all right. Good. How long will it take for the concentration of the insecticide to decrease to this? So it's the other way around. It's the other way around. So what we're going to need to do is take that same formula, insecticide at a given time equals the insecticide. It might just be easier to use the other form of this now. So concentration of the insecticide at a given time minus the natural log of the insecticide not equals negative kt. And we're looking for time. So divide this by negative k. No, not divide by negative k. Divide by k, negative on the entire thing. Should get us time. All right. So for that, what do we need to do? Uh, 3.0 exponent negative 7, the natural log of that, minus, where are you? 5.0 exponent negative 7, natural log of that, divided by k, 1.45. Negative version of that is 5. So 5 years. 5 years for it to jump down. Hooray. All right. The decomposition of dimethyl ether is a first order process. So again, we know it's first order with a rate constant of this many seconds. If the initial pressure is 135 torr, what's the pressure after 1420 seconds? So again, this is just like it was before. We know it's first order, so we're going to be using the natural log version of this. And we can actually use torr in this. Anything that can go directly into moles, you can do torr. Straight mass is not going to cut it, but density you can use that. So yeah, we can just use torr here. Okay. Yeah, I mean it's the same process as before. 135 is going to be our initial. We want to know what the time is after. So we know that it's let's just use A. A at a certain time equals A naught e to the negative kt. All right, so now we just kind of plug and chug. So 135 times negative 1.45 e equals 366. Okay. It is not that. I forgot to do one thing. I made a mistake on this one. I made a boo-boo. All right. So, negative 1.45 times. I was still stuck on the last one where our time was 1. Our time is now 1420. That's negative of that. We take the e of that, and then we multiply that by 135. Oh, that didn't change much of anything. And then, so yeah, 366 torr. Great. So that's that, guys. Hopefully this helped you out. I know distance like this can be hard. We'll get through it. I would say I'll see you guys on Monday. Unfortunately, my son was exposed and he is on distance learning, which means one of us, me or my wife, has to stay home on that. So just so you guys know, test is probably going to get pushed back from Monday to Tuesday. So Tuesday, Wednesdays are going to be the exams. Hooray! As far as well, I'll make another video for that. All right, guys, have a good one.